Hey everybody, welcome back to Calc 3 Online. So this is going to be the first of a few review videos for the course. And basically what I'm going to do in these videos is try to highlight what I think of as some of the most important concepts and problems from the course. So these are all kind of things that I really recommend you definitely know. And I think that they're kind of like the big takeaways basically from the course. So one of the things that we spent a lot of time talking about was, partial derivatives and just what those are and everything. But we also learned about this idea where you can find sort of the derivative in any given direction. So, we have partial derivatives where it's kind of like in the x directions. We have like f with respect to x, and then we can go in kind of the y direction. And that's f with respect to y, let's say. But we can also do like any other direction, right? We could do this direction, 4, 3. And that's where we get into directional derivatives. So one of the things you definitely want to kind of remember is like the kind of formula or like equation that we use to solve for directional derivatives. And basically it's like we use this notation, capital D, subscript U, f of like the point AB, let's just say, equals the gradient of f of AB dotted with u, where u is this unit vector, and this thing is like in the direction of v, okay? And basically what it's doing is it's really, this is sort of your derivative vector. And what we're really just doing when we do a dot product is we're sort of seeing how much of like this vector shows up on this or this one shows up on this. And by making it a unit vector, like taking v and normalizing it, making it a unit vector, you're not going to like add or like reduce the derivative amount, the instantaneous rate of change in that direction. It's just like a true measurement of how the function is changing in that direction. So that's kind of how this thing works. And so in this example, basically the first thing we got to do in any of these problems is get the gradient and evaluate it at the point. So f with respect to x is, I would think of honestly this as 1 plus x squared plus y squared quantity to the negative 1. And then just do the derivative that way. But whatever way you want to do the derivative, you'll have a chain rule in there. And so this will be 1 plus x squared plus y squared, and now it's raised to the power 2. And then f with respect to y is going to be very similar, except it'll be a negative 2y on top. And then 1 plus x squared plus y squared. And then you got to evaluate it at the point. So if you do f with respect to x at 1, 0, it's looking like the instantaneous rate of change in the x direction is negative 0.5. And then if you do y, you would get 0 actually, because you'll have a 0 up top, right? So now you just got to figure out, that's basically, so negative 0.5, 0 is like this vector. Now we got to get the unit vector. And if you think about it in terms of triangles, you're going like 4 in the x, 3 in the y. Those are the legs of a 3, 4, 5 triangle, right? And so really like the magnitude of this thing would just basically be 5. And so that's just, really I'm just finding v over the magnitude of v. And that's what u will be. And if you do that, you'll get 4/5 and then 3/5. And so now you can put it all together. So d in the direction of u of f at 1, 0 is just going to equal negative 0.5, 0 dotted with 4/5, 3/5. And so if you do that out, you'll get, negative 2/5. So negative 2/5 is basically the instantaneous rate of change of this function at that point in that direction. and doing directional derivatives is really about the most, in terms of derivatives, it's probably the most useful thing that we've learned, because it literally gives you a very concrete way of finding derivatives in any direction. Because sometimes these directions are not what you need. You might want that one and you might want that one, but you oftentimes need to know in a specific direction how much is the rate of change there. So that is directional derivatives, basically, in a nutshell. A very important idea from Calc 3. Another really important idea is doing these multiple integral problems, and ones where the integral is really messy and tricky, and how we can utilize change of variables to help us. So this is kind of one of the last things we did in chapter 15. This ties in with, this is basically where we're doing stuff with the Jacobian, and we're sort of just doing higher order U sub, right? It's basically, instead of just a U sub, which is used in a one-dimensional integral, you have to do like a UV sub or something like that, or a theta phi sub or something like that. So a lot of times the trickiest part is just knowing what to pick for your U's and V's. Just like even in U sub, it's hard to know what to pick for U, right? Hopefully, once you kind of do enough of them, you start to get better at it. And sometimes you just got to kind of jump into it and do like a little guess and check and try it. And it might not turn out so nice, and then you just try something else. It's the same thing with U sub. So when I look at this integral, one thing that just comes to mind is, well, what if I just took the top to be U and the bottom to be V? And the reason I'm thinking that is because I know that if I do a double integral of just U over V, those two things, like a du dv double integral, then is going to be a much easier double integral. Certainly the integral of U du is like really easy, and 1 over V is also really easy. So I'm thinking kind of ahead and trying to set it up so I would give myself an easier problem. So what I'm going to do is I'm going to do that. I'm going to let U equal 3x plus y, and then V equals 6x minus y. And what you really have to do in these problems first is get x and y. And so you have to take your U and V that you've chosen and write x and y in terms of U and V, right? And so what I'm going to do is basically going to set up a system of equations where I can try to eliminate x, and then another one where I can eliminate y. Eliminating y is pretty straightforward, right? Because we can see that if we just add these two equations, we would eliminate y. So let's just do that. So u plus v, right, is going to equal 9x. So x is equal to u plus v over 9. So that's going to be useful for us. To eliminate x, we would just want to multiply this by 2, and then we would want to subtract, right? So 2u, which equals 6x plus 2y. And then I'm just going to copy this down here. So basically, I'm going to subtract these two things, all right? I'll get 2u minus v, that'll be gone, and then 2y plus another y is 3y. So y is equal to 2u minus v over 3. So that will also be useful. So the next thing in these problems is basically to use my my x and y in terms of u and v. And what I'm really just trying to do is get a graph of what this space looks like after the transformation to the UV space, okay? And so first off, I need to know exactly, probably get a good picture of what that looks like. So let's do that. So basically here, let's see, it's looking like we would need 1/2, maybe 1, negative half, and negative 1. So we've got y equals 0, right? Which is the x-axis right there. Then we've got y equals negative x, which is going to be this line. Just put in a few points for myself. That line right there, right? And then we've got y equals x minus 1. So here's minus 1, go up 1 over 1, that kind of thing. So what color do I want? Let's do blue. So the other one, here. And so the region that, like the region R that I'm integrating over, is the bounded region formed by these 3 lines. So it's that region in there. So that's what I'm integrating over. And what I really want to do is that's it in normal XY space. I want to do the UV, do the transformation to UV space and see what these reduce to, post-transformation. That's the idea. So this is where we'll get into doing, utilizing this, but that part. So I'm trying to think about what color. Anyways, let's just do on y equals 0. So we'll do this one kind of first here. So y equals 0, right, that line, you're going to go over here, and you're going to be like, okay, y is equal to 0. So 2, u minus v over 3 equals 0, or 2u equals v. All right, and that's basically all we would really need to do. We just need to get it in terms of a nice equation that we can graph. And then let's just go and we'll do this diagonal line, y equals negative x. So for y equals negative x, y is 2u minus v over 3, and it equals negative u minus v over 9. So, negative x is just the negative of that. And then you just need to simplify all this out. And I know that you can do that. So I'm just going to jump to the answer part with this. So you get 7/2 u equals v for that part. And then last, we got the blue line here on y equals x minus 1, right? Y is 2u minus v over 3, and x is u plus v over 9 minus 1. Well, u plus v over 9 is x, and then we have minus 1. And then you just got to go through and simplify all that, There's a bunch of algebra. You do 5u plus, you get 5u plus 9 over 4 equals v. Okay, so this is telling me, basically what lines I get from these 3 lines after the transformation of UV space. And over here is actually those 3 lines graphed. You might have wondered what this was all about. But basically, for example, this 2u equals v, that is actually this red line right here. Okay. And then 7/2 u equals v is this one. And then the last one here, this green one, is actually the blue one. So what this has done for us is it kind of gives us a region that we can then use for bounds for u and v, which is going to be important, right? But the idea in these problems is that when we do a transformation like this to a new space, this is where the Jacobian thing comes in. So we have to sort of account for how the area, kind of a unit square of the area in the XY space changes post-transformation. And so that's where you do this partial derivative kind of determinant matrix. So what we need to do is take like the partial of x with respect to u, put it here, partial of x with respect to v, put it here, partial of y with respect to u, put that there, and then partial of y with respect to v, and put that there. And it's all pretty nice. If you do out the partials, you would just get a ninth, 2/3, and a -3rd. And so if you do that out, you're just going to get -1/9. But these problems, you got to remember, you got to use 1/9, okay? Really what we want is, we don't want the negative, we just want to know like the magnitude change, and the magnitude change is a ninth basically. So what that means is post-transformation, this little region is sort of decreasing in area by a factor of a ninth. That's what that means. At that point, we basically have everything set up to evaluate this double integral now. So I'm going to start putting everything in now. So we got double integral, and the top is u, the bottom is v, and I'm going to just do a du dv, all right? And you can see, here, I missed one thing, of course. I missed my Jacobian. I need a ninth in there because of the Jacobian. That's like the important extra little part, right? That's like the r in polar and the rho squares sine phi in spherical. And then I now have, this region based off of these reductions, basically, to get my bounds for u and v. So if you look at it in terms of the change in u, you go from, so at this point now we're just trying to use the bounds from here. And basically the way I would do this is I would split this into two, okay? So we can think of it, I guess you can think of it a few ways, but let's just think of it that way. So we're going to basically do this chunk in here, and then as a separate double integral, we'll do that chunk up there. And then we combine those together, and we'll have our answer, okay? So if you remember, this was v equals 2u. So that lower line, because we're going to go, so if you think about how we're going to integrate this, let me back up a second here. So this is u axis, and this is v. So if I was going to integrate over this blue region, I might want to go, because I cut it here, I might want to go from this line to this line, so blue to red, and then go from 0 up to 3.5, right? And do a similar thing here. Do from the green line up here to the red line, and then go from 3.5 up to 6, okay? So if you think about it, right, that red one was v equals 2u, right? And the blue one was, 7/2 u was equal to v. And so, if we're going to do du, if we're going to do du dv, we've got to switch the bounds, right? Because we've got v equals, and we want u equals, right? So this one would be like u equals 2v/7, and this one would be u equals v/2, right? And now these are what we can put in the bounds here. So we're going left, so we're going from the blue one to v/7 to the red one, which is just v/2. And then we're going to go in the vertical v distance, we're going to go 0 up to 7/2 or 3.5. It's a poorly drawn 7. And then, of course, that's just half of it, right? We've got to do the exact same thing, u/v, a ninth, du dv, And you got to do all that same stuff. You're going from 3.5 up to 6 now in the numeric integration at the end. So we're going 7/2 up to 6. And then in regards to the line, you're going to go from the green one to the red one. So we already have the u equals v over 2, which we can put up here still. But we would also have to write this one in terms of u equals instead of v equals. And so if you do that, you would multiply by 4, you would minus 9, then divide by 5. And so the lower bound here would be 4v minus 9 over 5. Now you finally actually have a thing that you can integrate. It's actually not a bad integration at this point if you do du dv, because I'll kind of show you maybe this one just quickly. If you do the double integral here, you're going to do u squared over 2, but we also have a 9th, so we can really think of pulling those constants out now as an 18th. And then we got a v, and then we're going to go from 2v over 7 to v over 2. Now we'll have dv. And then this is nice because, so I'm just going to pull that 1 over v out. You'll have v to the 4th. Nope, not v to the 4th. V squared. I was thinking ahead. V squared over 4. And then minus 4v squared over 49. But this is what's nice. If you have 1 over v here, it's going to cancel in there, right? And so you really end up getting a polynomial integral for the last one, which is really nice and easy. So basically that is your last integration you have to do, 0 to 7/2. If you do that all out, you get 11 over 192. And so that's one part of it. Maybe I shouldn't circle it yet. And then you would have to do the same thing here and add the two together. So if you do this one out, you get something that's about 0.04, let's say 5. And so then, just basically add those two together, and your final answer is about 0.10229, something like that. So I think that one's a good example of change of variables. There's a lot going on in these problems. They take a while to do, but they really are one of the definitely more important things from this course. Definitely want to make sure you know those.